Businesses nowadays accumulate large amount of data from their day-to-day operations. For example, purchase data are collected daily at checkout counters in Walmart, in Target, Macy's, etc. This figure shows the example of such data, and commonly known as the market basket transactions. Each row corresponds to a transaction which contains a unique identifier, transaction ID, and was bought by a customer. Businesses are interested in analyzing data to learn about the purchasing behavior of the customers. With the valuable information learned from the data, businesses can effectively provide marketing promotions to customers, manage inventory, as well as manage the customer relationship. In the example transactions, several association rules can be found. The first rule suggests that there is a strong relationship between the sale of diapers and beer. Many customers who buy diapers also buy beer. The second rule suggests that many customers who buy milk and bread also buy eggs and Coke. And the last rule suggests that many customers buy beer and bread together, also buy milk. The rules mean co-occurrence, not causality. Let's discuss the basic terminology used in association analysis. An item set is a collection of 0 or more items. For example, milk, bread, and diaper is an example of a 3-item set. And in general, a k-item set is an item set that contains k items. Support count is the number of transactions that contain a particular item set. For example, the support count for the item set milk, bread, and diaper is equal to 2. Because there are only 2 transactions that contain all 3 items. The support is the fraction of transactions that contain an item set. For example, the support for the item set containing items milk, bread, and diaper is equal to 2/5. A frequent item set is defined as an item set whose support is greater than or equal to a threshold. An association rule is an implication expression of the form X associated to Y, where X and Y are disjoint item set. The strength of an association rule can be measured in terms of the support and confidence. The support is the fraction of transactions that contain both X and Y. For example, in this rule, milk and diaper are associated with beer. Then the item set containing milk, diaper, and beer is searched to get the support count and divided by the total number of transactions, we get the support. The confidence measures how often items in Y appear in transactions that contain X. In the example, the support count for the item set containing items milk, diaper, and beer is equal to 2, and the support count for the item set containing milk and diaper is equal to 3. So finally, 2 divided by 3, we get 0.67, which is the confidence of this association rule. This page shows the formal definitions of those two metrics. Support is an important measure because a rule with low support may occur simply by chance. A low support rule is likely to be uninteresting from business perspective because it may not be profitable to promote items that customers seldom buy together. Because of that reason, support is often used to eliminate uninteresting rules. Confidence measures the reliability of the inference made by the rule. So the higher the confidence, the more likely for the consequent to be present in the transaction that contain the antecedent. Confidence also provides an estimate of the conditional probability of y given x. The association rule mining problem can be stated as follows. Given a set of transactions T, the goal of association rule mining is to find all the rules having support greater than or equal to a threshold, and the confidence greater than or equal to a threshold. The brute force approach lists all the possible association rules and computes the support and confidence for each rule, and then prunes the rules that fill the minimum support and minimum confidence thresholds. This approach is prohibitively expensive because there are exponentially many rules that can be extracted from a dataset. From this given set of transactions, a number of rules can be extracted with calculated support and confidence. It can be seen that all the rules are binary partitions of the same item set containing milk, diaper, and beer. And rules originating from the same item set have identical support but different confidence. So we may separate the support and confidence requirements. As mentioned, the common strategy by many association rule mining algorithms is to decompose the problem into two major tasks. In the first task, frequent item set generation, the objective of this task is to find all the item sets that satisfy the minimum support threshold. And in the second task, rule generation, the objective is to generate high confidence rules from each frequent item set, where each rule is a binary partitioning of a frequent item set. The computational requirements for frequent item set generation are generally more expensive than those of rule generation. A lattice structure may be used to enumerate all the possible item sets. This page shows such a lattice for 5 items, and in general, given D items, there are 2 to the D possible candidate item sets, including the null set. And because D can be very large in practical applications, the search space of item sets may go exponentially large. The brute force approach finds the frequent item sets by determining the support count for every candidate item set in the lattice structure. In order to do this, from the list of candidates, we compare each candidate against every transaction. And if the candidate is contained in a transaction, then its support count is incremented. This approach is very expensive because the number of candidates is very large. Given D unique items, the number of item sets is 2 to the d, and the total number of possible association rules can be calculated following this formula. The example is, if d is equal to 6, then the number of rules you can get here is 602 rules. As the number of items increase, the number of rules are dramatically increase as well. There are several ways to reduce the computational complexity of frequent item set generation. We can reduce the number of candidates, which is m. If we do complete search, then m is equal to 2 to the d, which is very large. Pruning techniques can be used to reduce m. We can also reduce the number of comparisons, which is n times m. N is number of transactions and m is number of candidates. With this method, we use efficient data structures to store candidates for transactions, and there's no need to match every candidate against every transaction. Now let's see how a priori principle reduces the number of candidates. The principle says, if an item set is frequent, then all of its subset must also be frequent. This principle holds due to the following property of the support measure. If x is a subset of y, then support of x is greater than or equal to support of y. And this is known as the anti-monotone property of support. Let's look at the illustration of the a priori principle. If if an item set is frequent, then all of its subsets must be frequent as well. In this illustration, if CDE is found frequent, then all the subsets are frequent as well. In another illustration, if the item set containing A and B is found to be infrequent, then all the supersets are also infrequent and they can be pruned. And this approach is very effective because you don't need to count the support of the rules to prune them. This slide shows the illustration of the frequent item set generation of the Apriori algorithm. At the beginning, every item is considered as a candidate one item set. And here we assume the minimum support is equal to 3. So after counting the support of the one item set, the two candidate item set containing Coke and the one containing X can be discarded because they have fewer than 3 transactions. In the next iteration, candidate 2 item sets are generated using only frequent item set from the first step, because the priori principle ensures that all the supersets of the infrequent one item set must be infrequent. And because there are 4 frequent one item sets from the first step, so the number of candidate 2 item sets generated is the combination in which we get 2 out of 4, which give 6. At this step, 2 item sets, bread and beer and milk and beer, are infrequent by computing the support and can be discarded. So the rest with 4 item sets are frequent and then can be used to generate the 3 item set in the next iteration. This page shows the frequent item set generation for generating item sets, frequent item sets in Apriori algorithm. So the method is, at the beginning, let k equal to 1 and generate frequent item sets of length 1. And now comes the loop. Repeat until no new frequent item sets are identified. And in each iteration, generate length k plus 1 candidate item sets from length k frequent item sets, and prune candidate item sets containing subsets of length k that are infrequent. Then count the support of each candidate by scanning the database and eliminate candidates that are infrequent and leaving only those that are frequent. If the minimum support is set too high, then we can miss item sets that involve interesting rare items. And if it is set too low, then it's computationally expensive and the number of item sets is very large. So using a single minimum support threshold may not be effective.